After studying this module, you shall be able to know the significance of irreversible thermodynamics, differentiate between equilibrium and non-equilibrium thermodynamics, learn postulates of non-equilibrium thermodynamics, and know about different laws of thermodynamics, that is first, second and third law. Introduction. In the classical thermodynamics, we have seen time-dependent variation of thermodynamic quantities such as internal energy, enthalpy, entropy, Gibbs free energy, etc. are not considered. Classical thermodynamics deals with transition from one equilibrium state to another, which brought about by different mechanical or chemical methods. It is not applicable to systems in which transport of heat, charge or matter takes place. Non-equilibrium thermodynamics is that branch of thermodynamics that deals with the system which are not in thermodynamic equilibrium, but such systems can be described by non-equilibrium state variables, which represents an extrapolation of variable used to specify system in thermodynamic equilibrium. All natural processes occurring are not in thermodynamic equilibrium or irreversible in nature. Systematic macroscopic and journal thermodynamics of irreversible process are obtained from Onsager theorem. Irreversible thermodynamics essentially deals with the qualitative and quantitative changes occurring with respect to time. Many physiochemical processes which are typically known as irreversible process include conduction of heat, diffusion of matter and chemical reactions. Now let us know about the difference between the equilibrium and non-equilibrium thermodynamics. One basic difference between equilibrium and non-equilibrium thermodynamics lies in the behavior of inhomogeneous systems, which require knowledge of rate of reaction, but this is not considered in equilibrium thermodynamics of homogeneous systems. Time courses of physical processes are ignored by equilibrium thermodynamics, but irreversible thermodynamics explain the time courses of physical processes in continuous detail. Consequently, equilibrium thermodynamics permits those processes that pass through states far from thermodynamic equilibrium that cannot be described even by variables admitted for non-equilibrium thermodynamics like time, rate of change of temperature and pressure. Equilibrium thermodynamics use the concept of quasi-static process. A quasi-static process is conceptually timeless and physically impossible mathematical passage along continuous path of states of thermodynamic equilibrium, but this concept of quasi-static process is not used by non-equilibrium thermodynamics. Non-equilibrium thermodynamics states that continuous time courses need its state variable to have a very close connection with those of equilibrium thermodynamics. Now we will see the postulates of irreversible thermodynamics. The total entropy change ds of a system can be expressed as the sum of entropy change arising from system and its interaction with the surrounding. Therefore, we can write ds total is equals to the sum of ds external plus ds internal, where ds external is the entropy change due to surroundings or external system. ds internal is the entropy change within the system, that is internal system. ds total is the total entropy. Entropy change within system can be equal or greater than 0. Therefore, we can write ds internal is equals to 0 in reversible system or equilibrium system. ds internal is greater than 0 in irreversible processes or non-equilibrium system. If ds external is equals to 0, then ds total is equals to ds internal, which is greater than or equal to 0. There is no restriction on the sign of ds external, but ds internal should always be positive for irreversible thermodynamic states. The quantity Tds internal is called uncompensated heat by Clausius. The next postulate is the local entropy production sigma is defined as the sum of product of fluxes and conjugate forces. The entropy production could always be isolated for any process. It is also equal to or greater than 0. That is, your sigma is always greater than or equals to 0. For the reversible process, entropy production is equal to 0. The dissipation factor Xi is defined as T sigma, where T is the absolute temperature. Xi is positive dissipation as it is natural consequence of irreversible process. Sigma can also be represented as ds internal by dt. Onsager formalism of irreversible thermodynamic states that the entropy production dissipation function can be represented as sum of fluxes and their conjugate forces. That is, sigma can be written as summation of ji into xi, where ji is the force of ith component, xi is the flux of ith component, and n is the total number of fluxes that are possible in a given system. The linearity between the fluxes and forces can be assumed to be valid as a first approximation for large class of systems. In near equilibrium region, Ji is equals to summation of the product of Lik into Xk from k is equals to 1 to n, where Lik is the phenomenological coefficient. Xi is equals to summation of product of Rik into Jk from k is equals to 1 to n, where Rik is the resistance or resistivity coefficient. Now let us know about the non-equilibrium state variables. Non-equilibrium thermodynamics needs its state variables to describe continuous time courses so that it can connect to equilibrium thermodynamics. Non-equilibrium state variables are measured locally with same technique which are used to measure thermodynamic state variables. These state variables are spatially and temporally non-uniform. Because of this spatial non-uniformity, non-equilibrium state variable that correspond to extensive thermodynamic state variable are need to be defined as spatial densities of the corresponding extensive equilibrium state variables. Occasionally, when the system is close to thermodynamic equilibrium, then intensive non-equilibrium state variables approaches equilibrium state variables like temperature and pressure. Moreover, non-equilibrium state variable should be mathematically related to each other in ways that resemble corresponding relations between equilibrium thermodynamic state variables. Now let us see the basic concepts which you have learned earlier also. System exhibiting non-equilibrium processes are much more complex then they undergo fluctuation of more extensive quantities. Some boundary conditions which are imposed on them, particularly intensive variables like temperature gradient or distorted collective motions, are called thermodynamic forces. Now discussing different laws of thermodynamics. Zeroth law of thermodynamics. Zeroth law of thermodynamics states that if two bodies A and B having different temperature, when come in contact with each other, they both attain same temperature. In such system, Mass won't get exchanged, but energy is exchanged. Thermometer is based on Zeroth law. First law of thermodynamics. The first law of thermodynamics is also known as law of conservation of energy. That is, energy can neither be created nor be destroyed. This law states that if system absorbs heat from the surrounding, internal energy of system increases. This rise in internal energy can be given back to surroundings in the form of work. Mathematical form of the first law is Q is equals to delta U plus W, where delta U is a change in internal energy, Q is the heat absorbed and W is the work done. We also know that the work done is given by P into delta V. Substituting this equation in equation we get Q is equals to delta U plus P delta V. Now the heat absorbed keeping the pressure of system constant will be given by Qp is equals to U2 minus U1 plus P into the difference of V2 minus V1, or we can write Qp as equals to U2 plus PV2 minus U1 plus PV1. In the equation, U denotes the internal energy, P is the pressure and V is the volume. All three of them are the state functions. Therefore, the quantity U plus PV should also be the state function. The quantity U plus PV is equals to H is known as enthalpy, and the change in enthalpy will give amount of heat absorbed at constant pressure, that is Qp is equals to delta H. Now let us see the second law of thermodynamics. The second law of thermodynamics forms the most important law in classical thermodynamics, from which the criteria of spontaneity and equilibrium of a system are derived. From this law, it can be deduced that at equilibrium, entropy of an isolated system reaches maximum. At equilibrium, sum of all the components of entropy change is equals to 0, that is, summation of dSi is equals to 0. For spontaneous reaction, which is moving towards equilibrium state, the sum of all the components of entropy change become greater than 0, that is, summation of dSi is greater than 0. In the steady state condition, macroscopic properties like pressure, composition remains the same with time, but dissipative processes continues to change in a system. Infinitesimal change in entropy is defined as ds is equals to del q reversible by T. For spontaneous process, it is defined as ds greater than del q by T. Now we will see the third law of thermodynamics. The third law of thermodynamics states that the entropy of a perfect crystal of any pure substance becomes equal to 0 when the temperature is absolute 0. At this 0 temperature, the system must be in state possessing minimum thermal energy. This system is correct only when the system has one state with minimum energy. Thus, at absolute 0 temperature, the state is of perfect order, that is 0 disorder and hence 0 entropy. Therefore, when temperature becomes 0, S is equals to 0. The relation between entropy and the number of microstates possible for a system is given by S is equals to Kb ln omega, where Kb denotes the Boltzmann constant and omega is the thermodynamic probability, which is the number of microstates corresponding the given macrostate of the system. This equation is known as Boltzmann entropy equation. It gives the quantitative definition of entropy as disorder. Now let us summarize what we have learned. Thermodynamics of irreversible processes essentially deals with the qualitative and quantitative change occurring with respect to time. It is concerned with the transport processes with the rate of chemical reactions. Equilibrium thermodynamics use the concept of quasi-static process, whereas non-equilibrium thermodynamic does not use the concept, rather needs state variable to describe continuous time courses. Total entropy change of system is the sum of entropy change which arises from its interaction with surroundings and entropy change within the system. The local entropy production sigma is the sum of product of fluxes and conjugate forces and is therefore given as the product of Ji into Xi, where Ji is the conjugate force, Xi is the flux and N is the total number of fluxes.